Hi, good morning, everyone. Welcome to our second to last lecture of the semester. I hope you're doing well out there. Hang in there, it's almost over. So, today we're going to be talking about exoplanets. I know we talked about these a little bit earlier in the semester. Today we're going to focus on the different methods that we find exoplanets or exoplanet detection techniques. Before we move into that, I should say that we do have one last homework assignment, and this will be due on Wednesday of finals week. I want to make sure to get that in there so that we can have chapter 11 on the final exam. So the final exam will be Friday of finals week, and that will cover chapters 10 and 11. I'll have some more details coming on Friday for that. All right, so let's jump into today's lecture. Here's a question for you. Which statement is correct? So please go ahead and push pause. Think about this quietly on your own. All right, it turns out that the correct answer here is C. Jupiter and the Sun orbit a common center of mass. So if we take a look at that real quick, we have the Sun here and Jupiter here, and the center of mass would be somewhere inside the Sun. We can think about this like a fulcrum, like a seesaw, where we have Jupiter over here and the Sun over here, and in order to balance these two, we've got to have this center of mass, or a fulcrum. And Jupiter is about 1,000 times smaller than the Sun, so there's about a ratio here of about 1,000 to 1 when it comes to the mass. And so that's why the fulcrum, or the center of mass in this case, needs to be so close to the Sun. And then the Sun would orbit around the center of mass, and Jupiter would also orbit around the center of mass. So let's take a look at that some more. So up in this upper picture, you can see the Sun here and Jupiter, and here's the center of mass. In this picture, they've drawn it right at the edge of the Sun, but it's really inside the Sun. And if we look here, as Jupiter goes through half of its orbit, the Sun also goes through half an orbit about that center of mass. So that's a half an orbit for both of those. And so the Sun wobbles back and forth depending on how we're looking at it. So it's wobbling around. It doesn't really look like an orbit, it more just looks like a wobble. Now we get tugs from not just Jupiter, that's the largest planet, so it has the largest effect, but there are tugs from all the planets, not just Jupiter, and they cause the Sun to wobble. So it's really this combined effect that we would see, and that's what this picture down here is. You can see the center of mass right here, and this is the Sun's position over about the last 50 years or so. Well, starting in 1960 here, so the last 60 years. And you can see that the Sun makes this fairly complicated orbit around the center of mass, depending on where the other planets are. Just for scale here is about a half a milli-arcsecond, and this is the radius of the Sun if you were looking from 30 light years. So remember, the closest star is about 4 light years away. So this is about, 10 times farther than the nearest star. And so this is barely wobbling around about the size of the Sun. So these are very small wobbles. They're hard to detect. but it's doable. And we've actually found thousands of planets by looking at this wobble and at other ways. So, there are a couple of methods that look at this wobble. Let's talk about some of those. All right, so here's another question for you. Which exoplanet detection method indirectly detects the wobbling motion of the star? So keyword here is indirectly. Please push pause, think about this for a moment on your own. All right, it turns out the correct answer here is the Doppler method. Now we'll go into some detail on that in a minute. That's looking at the spectrum of the star. Before we move on, though, I just want to mention that this also looks at the wobble. But directly. So it directly looks at the motion of the star, the host star we'll call it. And this looks at changes in brightness of the host star. And this method here has to do with how the star and the planet warp space. We're not going to cover that here. But it is an interesting method. Gravitational microlensing has to do with Einstein's theory of relativity, something I would encourage you to look into. So before we move on and talk about these methods in detail, I just want to mention that the first exoplanet around a main sequence star was found in 1995, and this used the Doppler method. So that was the first one, and since then, I just checked this morning, and there are roughly 4,000 exoplanets. I should say confirmed exoplanets. That means they've gone back and verified those detections, either with a second detection or a second method. And the vast majority of those were found using the transit method. And that was primarily with the Kepler mission. So that's something you should look into if you're interested in this topic. All right, so let's look at a little detail on the astrometric method. I just want to highlight a few things here. So astrometry means measuring star positions. So it's just measuring the positions of stars from night to night. So we could have a star here. We're observing it. Here's the observer, and we see it right here in the sky, maybe relative to some other background stars that are not moving. And then we go out another night, and we see that star over here, and we've noticed that it's moved over. And so that's astrometry in a nutshell. So by looking at the positions of the stars, we are directly imaging the wobbling motion. Now, this is limited. Only the nearest stars can this method be used by, because we have to be able to measure those changes in position, and that's very hard to do. And this has a little bit of a bias, is that it's easier to see the wobble for distant planets, but the wobble is slower. It also is easier for big planets. The bigger the planet, the bigger the wobble. One thing I want to mention right now is that there's two ways of viewing these systems. One is called face-on, where if we look at the planet going around the star, it would look like a circle. That would be face-on, and this would be good for the astrometric technique. The other way of looking at these is called edge on, and that's where the star is here and the planet moves back and forth in the plane of the sky. And so the astrometric technique works good for both of these. For both, how do I want to say this? Both inclinations. Inclination just means how is that orbit tilted relative to us. So it works for both inclinations. You could see here the star would wobble around this way, and here the star would wobble back and forth. We could measure both of those wobbles, assuming it was a big enough wobble and the star was close enough to us. So that's some of the limitations there. Now let's look at the Doppler effect. This is also or Doppler technique. Before we get to the technique itself, I just want to mention the Doppler effect a little bit in and of itself. So the Doppler effect, this is where the light from stars or sound from a car or a moving train, as we can see below, if it's moving towards or away from the observer, whoever is hearing the sound or seeing the light, it's called blue shifted or red shifted. So the example down here with the train that's either stationary or moving, that's there because this is something you're familiar with. This is the classic race car sound. I'm sure you guys have heard and probably made that noise before. So as the train or the race car is moving towards you, it makes a higher pitch sound. And so that higher pitch is because the sound is shifted to high frequency or short wavelength. If it's moving away from you, the other part of the sound, it goes to lower frequency or higher wavelength. Now with sound, we typically just talk about that in terms of frequency or tone. With light, we often talk about it in terms of the color. So if you remember our spectrum, we have Roy G. Biv, red, orange, yellow, green, blue, violet. Well, if light is shifted to over here, these are short wavelength and high frequency, and these are long wavelength. That if the light is shifted to shorter wavelengths, we call that a blue shift because it's towards the blue part of the visible spectrum. If it's shifted towards longer wavelength, we'd call that red shifted because it's shifted to the red part of the spectrum. So it turns out that light, which is also a wave, behaves just like sound with respect to the Doppler effect. And so if this light source is moving towards the observer, those light waves are shifted to higher frequency and shorter wavelength. So these are blue shifted toward and red shifted away. And so we can observe the spectrum of the star and see if it's moving towards or away from us. And so that's what you see down here in this picture. As you can see that star as it's going around, around in its orbit. As it moves around this part of its orbit, it's moving towards us, and that light would be blue shifted. As it's moving in this part of its orbit, it's moving away from us, and that light is red shifted. And so if we look at part of the spectrum, what we would see is that it's moving towards and away, and we can turn that into figure out how fast it's moving, and we can make graphs like this where we can see that star moving towards and away from us. See here its velocity, and so we can measure those radial velocities. So this is often called radial velocity method. Okay, so this is an indirect image of the wobbling. We're not actually measuring the wobbling, we're just measuring an effect of it using the Doppler method. This also works well for larger planets because we get larger tugs, and so there's a bias here. It's better at finding larger worlds. It's also better at finding shorter period planets, just like the astrometric method. So these are similar in that regard. We do need large telescopes, and here the inclination matters. This is only going to work. This only works for edge-on systems. So we have to see it moving directly towards or away from us. If it's a face-on system, it doesn't move towards or away from us, just left, right, up, and down. All right. So that's the second method that observes the wobble, and we can measure, here you can see we can measure its period, or how often it wobbles. That's the same thing we can measure with the astrometric technique. As we measure it moving around in the sky, we can figure out how often it goes around. All right, here's the third and final method we're going to talk about. This is called the transit method, and transit is a word for an eclipse. And you can see that right here. What we're looking at, oops, I spelled that wrong, is the planet passing directly in front of the star. So first off, you can see that this needs to be an edge-on system because the planet and the star have to align with one another. And we actually end up with two transits here. We get one transit where the star or the planet passes in front of the star. We call that the primary transit. You can see that here. Here's the starlight as the planet passes in front of it. It blocks out some of the light for a little bit, and then it comes back to normal as it moves out of transit. By looking at how long this takes to block, we can get a pretty good estimate of the size of the planet, which is pretty cool. We can start looking at their physical properties. Now, here, not only do we have the primary transit, we have a secondary transit where the planet now goes behind the star, and it actually blocks a little bit of light from the star. From the planet. What we're really seeing here is the combined light of both the planet and the star. And so as the star eclipses the planet, there's a little bit of a secondary dip here, and that helps us get more information about it. Now, this method is very, very difficult. A sort of analogy here is this is like a fruit fly flying in front of a 100-watt light bulb 3,000 miles away. So it's like looking at like a fly passing in front of a light bulb in New York City. So you have to have very, very good telescopes, and you pretty much have to be in outer space to do this. So the Kepler mission was designed to do this. It looked at something like 14,000 stars for 2 years and was able to find thousands of these planets this way. So here's a little more information on that with some details. Stars, here's the Kepler mission I was just mentioning about, and it looked for 4 years, and it looked continuously at 170,000 stars, and it found roughly 2,000 exoplanets. I think that number's higher now. This slide is from 3 years ago. A lot of these possible candidates have been moved over into the confirmed as they've analyzed the data. One thing to point out here is stars naturally vary with time. They get brighter, they get dimmer, and so we really need to find sophisticated ways to find the signal of the planet and not just the variability of the star itself. I know that caused some problems. Kepler had planned to look at stars that were like the sun-like stars, and what they found is the sun is an unusual star. It's not very variable. The brightness of the sun doesn't change very much compared to other stars that are the same mass. And so that was a big problem for the Kepler mission. All right, the last thing I want to talk about is what properties do we get from these. So again, please push pause and take a moment to think about this on your own. Which exoplanet method allows us to determine the size of the planet? All right. Well, it turns out that the correct answer here is C, the transit method. Remember, by blocking the light, we can see the size of the planet. All right, so here's a table of that, and I just want to point out a few things on this table before we wrap it up for today. Some of the planetary properties, the orbital properties here that you should pay attention to are period and distance. These are the ones you should know, and these are actually found by all three of these, because this one, we're just looking at timing. So taking measurements over a period of days, weeks, years, we can figure out how often the stars wobble or how often they dim because of these eclipses. And so with all of these, we can find the period P. Now, once we know the period, we can calculate the distance. Remember Kepler's third law, P squared equals A cubed. So this is the semi-major axis. And so again, if all three of these can find the period, all three of them can find the distance from the planet to the star. Now, the other properties I want you to remember and pay attention to are the mass and the size of the planet. Now, the mass we can get from the astrometric or the Doppler method, and this is because we can look at the motion of the star. How much is it wobbling? We're looking at the planet's tug. And the greater the tug of the planet, the greater the motion of the star. And so we can get a really good estimate for the planet's mass by how much it's pulling on that star. Now with the transit method, we don't see the star moving, so we have no idea how much that planet is tugging on the star. Although we can get the size, we just talked about that because we can see it blocking the light. And so this is from blocking the light, and by looking at how much light's blocked and how quickly it gets blocked, we can see the size. And then we can combine those two and get the density. So as long as we can have the mass and the size, remember density is mass over volume, and so we could calculate that. But if you can remember these four properties and which methods can identify them, I would be happy with that. All right. Well, that's it for today. On Friday, we're going to wrap up our discussion. We'll wrap up the whole semester on Friday, but we're going to wrap up our discussion of exoplanets. We'll talk more about the properties of exoplanets and the types of planets that we've been finding with these various methods. And that'll be it for this semester. So I think this is a nice place to stop. We won't get into some of the more esoteric stuff at the last few chapters, but I think we did a really good job of covering some basics of astronomy, where we might find life in the solar system and where we might find life outside of the solar system. So again, thanks for hanging in there, and I will, quote unquote, see you Friday.